is hyperspectral optics and remote sensing in the PACE era. And I was kind of reviewing, I was looking through the slides I had and reviewing a lot of the work you've probably done in the past week and a bit. You've been looking at hyperspectral sensors, hyperspectral field measurements. So there was a lot of that sort of fundamental measurement that I didn't really think probably was worth redoing, lest you fall asleep. So this one will be very much a PACE-focused talk, which is close to my heart. So, but I'll start by just giving you a little bit of a history lesson. I don't know if you've the history of ocean color, and maybe I'll do my best and just sort of technologically sort of step you through where we ended up. Then we'll talk about the mission, the payloads and how they work, the data products, how we're validating, and sort of the whole overview of the mission. So I guess for the people in this room, sort of PACE will be what MODIS was for me, which was CWIS was for the people before me. So exciting times ahead. So let's wind the clock right back to who's heard of the well, I like to say CZCS, but it's CZCS. Who's heard of CZCS? Who's used CZCS data? Okay, so CZCS was kind of like this groundbreaker. I call it the groundbreaker because prior to that, let's just go and look at the picture. Nice picture down the bottom right-hand side. That's an entire mission composite. For the whole period from 1978 to 1986, all the data that CZCS collected, composited into a global map of chlorophyll. What do you think what did the ocean, or what was our understanding of the distribution of chlorophyll in the global ocean before that? What did those maps look like? They were hand drawn. Yeah, so I couldn't find one to put in. I think it's in one of my old sort of history books on ocean color, so I didn't have it handy. But yeah, you see these contour plots. This is what we think the chlorophyll looks like in this part of the ocean. So we see these kind of maps and simulations now. It's just like bread and butter. You go, yeah, that's what it looks like. But beforehand, it was kind of like a bit of a unknown. So it was a huge deal to just get this map out at the end of the mission. And before that, this was also ocean color science. We're running a training course for 2 weeks, but before this mission, it was all theoretical and in situ based. And apparently the proponents of this mission had a big push to actually get it over the line because there were a lot of naysayers saying, no, you can't see chlorophyll in space, can't be done. So they had some airborne campaigns that sort of showed, yeah, it looks like there's some changes, and they went ahead. Anyhow, so I put a CWIS image there, that sort of to take us into the next slide. There was a limited sensor. We only had 4 bands. Now we're up to PACE with hundreds of bands, and you only had one near infrared channel, which was supposed to be to help you with the atmospheric correction. And if you recall from yesterday's Monday's talk, David was discussing the atmospheric correction. So does anyone recall how many near infrared bands we should have to select our aerosol model in the atmospheric correction? In more than 1. 2 at least. You want 2 at least. So they were limited with how they could atmospherically correct this data. They had a thermal channel on there, but that kind of flaked out in the early days. And it was a scanning mirror, so it kind of you project the Earth image up onto a mirror, and it would spin and reflect that back into the optics to image it up. Signal to noise ratio. This is a thing that we like to think about with ocean color. Does anyone know signal to noise? Have we spoken about that in the last couple of weeks? Who can sort of tell me a little bit about signal to noise or wants to volunteer? Yeah, over here. Yeah. That's an important point. That's what I was going to say. I like that, the input radiance. So is the ocean a dark target or a bright target? Who says dark? Who says bright? Good. I think majority said dark. So yeah, the ocean is a dark target. So you need very, very sensitive sensors to measure it with, which means that what we call the L typical, the typical radiance coming up from the ocean is dark. So we need high signal to noise, so we don't end up with a really noisy spectrum. So anyway, yes, yeah, on orbit. Yes, yeah, that was on orbit. Yeah, exactly what was described. We look at a very uniform part of the ocean, say this the gyres, and you look at the an area which is optically and aerosol-wise quite homogeneous. So Chuan Min Hu has written a paper on that a few years ago, actually, for MODIS and CWIF. So yes, it is possible. Yeah. So anyway, there are limitations. Big issue, because that was an entire mission composite that we can get in a few weeks, in like a month now, of the global ocean, and it was data storage and downlink. So imagine you go back to 1978. How do you think computer infrastructure was? Like, I think my iPhone's probably more powerful than their supercomputer was in those days. And downlink of data was very slow and arduous. And they actually used to put the data from these on big tape drive, big discs, and physically drive them from one lab to another. So they'd be in the trunk of some person's car while they're driving around. So you talk to Gene Feldman about that. I'm sure he'd tell you a full story. So anyway, moving on to CWIFs. Lovely CWIFs was just a game changer. It was actually designed to be dedicated for ocean color. There were the lessons we learned from the CZCS that sort of fed into the mission. And it was designed to have higher signal to noise ratio. We had what's called a rotating telescope design, which meant you had a single science pixel as you scanned across the scene, and a nice wide swath, not as wide as some of the more modern sensors, 1500. And importantly, I think for this mission it was continuous capture. So it was just recording data and downlinking it the whole time. So it meant you were able to build up these global images as you went. Some important advancements with the sensor was you had two near infrared bands now, so you could improve that atmospheric correction. And you had fore and aft tilt. CZCS did tilt as well a little, but it meant so sun glint. People familiar with sun glints? John talked about it the other day, or yesterday. Yeah. So sun glint. One way to mitigate sun glint is to tilt your sensor. It's a bit like if you're looking at a sun reflecting off a surface and you turn your head away, and there's it's not so glary over there. That's the sort of the principle. So as you come up over the equator, the sensor will tilt and sort of view away from the ocean. So CWIS was a big advancement, and essentially the actual PACE sensor is very similar to this, except it's hyperspectral. So something that was designed in 1997. Obviously, the optics and everything had to be advanced, but the principles are very similar. Okay. Oh, yeah, sorry. And there's some other things here that sort of CWIFs drove the community to sort of innovate, and they had this Symbios program at NASA, which was a validation program. So they came up with, there was new instruments came out of it. There was validation protocols. There was software for processing. So CDAS, which we'll talk about later. They came up with ways of calibrating the sensor on orbit, looking at the sun, looking at the moon, and a number of the instruments that sort of emerged with these multispectral instruments for the field came out of these programs. But we didn't go, a lot of the sensors in those days weren't in situ sensors, weren't hyperspectral necessarily, because we had a multispectral sensor, and also just limitations with what we had. And one other limitation was onboard storage with, I should mention, with CWIFs. You had to have these downlink stations dotted around the world, and people, it was actually an interesting setup. I'll talk about that more if I have time. But anyway, moving on. MODIS, the juggernaut. I also heard juggernaut because it's not. I look up the definition of juggernaut, and it's sort of like something that's vicious and smashes things, and but it keeps going. Maybe I should have said the Energizer Bunny. Just MODIS just keeps going. It just won't stop. Will stop soon, but been going for like over 25 years now. There's one on board the Aqua spacecraft, one on board Terra, which launched earlier. And they kind of have about, yeah, I'd say about 9 ocean color bands. There's these 1 kilometer pixels. But what was neat about Modus was they also had these land bands that who was going to correct me. Yes, I actually saw that too. It came up and I was like, oh, I hope it doesn't translate to be something like offensive. No, Lord of the World. Well, maybe. Well, it's been going for, yes, maybe Modus has been going for 25 years. It's been looking at the world from up on top probably longer than any other sensor. So maybe that works. I'm just sort of thinking of an unstoppable beast because it just keeps going. Good Goddard spacecraft, that one. So yeah, it was a nice sensor. We had these land pixels at 250 meters, and you could do some ocean color science, so coastal work with those. We and you had near infrared and SWIR channels. So with the SWIR channels, it meant you could do atmospheric correction in sort of more optically complex waters. And it didn't have a rotating telescope design. So a rotating telescope was a bit like, like a clothes dryer that's silver inside. Like if you're thinking of drying your clothes or a washing machine, and it's silver inside, and it's basically that's what a rotating telescope is. It's basically essentially a circular mirror, and your light comes in and reflects off that mirror into the optics. Whereas with Modus, you had a two-sided mirror, and it spins. So it's like a big one, like a paddle that flips over. So as it's rotating, you're looking at the Earth, it's rotating, and as the image is being sort of reflected into the optics, and then it would flip over and take another scan. But what do you think happens if you don't characterize both sides of the mirror properly? You sort of get these strips. One mirror create as it's moving along. The sensor's scanning and building up a picture, and so if there's any differences in the calibration or sensitivities on either side of the mirror, you start to get these strips or striping cross track that you would see. And in Modus Terra, that was particularly challenging because both sides of the mirror had different polarization sensitivities. Again, CWIS didn't have that problem because we had something called the polarization scrambler inside, so it wasn't so sensitive to atmospheric polarization. So had multiple detectors. Nice thing about Modus, nice big swath, so you could see a lot more of the Earth more frequently, and it had about a 2-day global capture as well. So yeah, good. Just keeps going, but not for much longer. They're about to deorbit Modus in the coming years. Probably needs a nice retirement. Unfortunately, the retirement for spacecraft is they get burned up over the Southern Ocean. But the good thing was we were able to extend beyond chlorophyll. We started doing IOPs, phytoplankton community composition. We started to advance beyond just looking at bulk chlorophyll. And then we saw the advent of some new in situ technology as well. These hyperpros, which are like a hyperspectral radiometer for field validation. They had the AeroNet OC network started to pop up. So it was a aerosol. I don't know if we talked about AeroNet OC. I won't go into it, but it's an aerosol ocean color remote reflectance sort of platform that they put in dotted around the world for validation. And with Modus, just an explosion in the literature. So I just Googled it. I just put a Google Scholar search in the other day for Modus ocean color. And it's something like it was nearly 100,000 results came back. So just mentioned it in articles. So I don't know, maybe that counts a few duplicates, but it's a lot. The so-so, I like to say the so-so because I'm being recorded. I don't want to say I don't want to say terrible or bad, but things that you could do better is that if you're thinking purely from the ocean color science perspective, which that's my background, Modus was like a shared discipline mission. It was to do, there was parts of the sensor that were designed to do land. That were those 250, 500 meter bands, and their signal to noise wasn't optimized for the ocean. So there were parts of you had to play some games to get those spectral channels to work well in the ocean, whether you aggregated them up spatially or temporally or whatnot. You also had, I didn't put a picture of it in, but there was multiple detectors for each channel. So when your mirror scanned across the scene, you might be looking at something like there was 16 pixels within this like strip. So you had to characterize a lot of different detectors. Well, that's what I'll just say. There was a lot of different detectors that had to be characterized, and that can be challenging. And I think probably one of my biggest bugbears was it didn't tilt. So you lose a lot of data in the equatorial north regions because you're just losing all this data to sun glare. And again, um, that's probably a consequence of being a shared and multidiscipline mission. The terrestrial community does not like their spacecraft to tilt. They like to maintain the same geometry, but they don't have the same issues with glint as we do. So there's usually more of them than us. Okay, so moving into the era now of the VIIRS spacecraft, and VIIRS is it's like a NOAA NASA they call it a joint polar partnership. Can't remember the acronym, but it's a partnership between NASA and NOAA to kind of operationalize the ocean color, but as well as some of these legacy land and atmospheric products that MODIS has been driving for a long time. I guess the thing to note was we didn't advance much beyond MODIS with VIIRS. We'd reach a mature state in the science, but spectrally we're only really looking at 5 spectral bands. When you think about CWIFs, it was 6, so maybe just a little bit incremental decline. I don't know. Don't record me saying that. But the cool thing about VIIRS was it had a really wide swath. You can almost get daily coverage with VIIRS, but with ocean color, when you start to get to the edge of the swaths, your atmospheric correction tends to get a bit weird because you're looking through a really long wedge of atmosphere. So we tend to trim off sides of those wide swaths. Anyhow, MERIS is another one, and ULTRI. They're from EU. EU METSAT and ESA. MERIS was operational for about 10 years, sort of overlapped well with MODIS Aqua. And ULTRI and the central programs are sort of this new, again, it's a bit like VIIRS, it's a multi-mission sort of continuity approach where you have the same sensor aboard multiple spacecraft. For MERIS, what was cool was it had natively it had 300 meter pixels, so you could do a lot of coastal nearshore work really well, or you could bin it up for the ocean. As with a lot of going back in the Wayback Machine 10 or 20 or 25 years ago, we have to remember computers weren't as fast, internet wasn't as fast, downlink technologies weren't as fast, so you were kind of limited by these bandwidths of how many spectral channels you had and what the pixel size was. So there was a bit of a trade space. So that's why you sometimes see these sensors that had full resolution might have a local downlink station somewhere, and it might be a regional data collection. But once you got to the global scale, they were binning up to a larger pixel size on the spacecraft, so to save memory and be able to downlink the global the global data set. But what I mentioned was Wayne talked about gratings and prisms. So I'll pick up. Someone tell me about gratings. What does a grating do? Or a prism? What's a prism do? Takes white light and separates wave. So essentially, a lot of it is a grating instrument. Wayne did mention pace. So the light, the signal would come through, go through a grating spectrometer and split the signal into different, basically hyperspectrally onto a focal plane. So really on the actual sensor, MERIS and ULTRI kind of hyperspectral sensors, but then they aggregate those channels to multispectral on the fly to boost signal to noise. So yes, interesting thing about MERIS though was it was the band, because of that design, you could program which bands you wanted. You might choose a different spectral aggregation. I don't think in practice it was ever really done. The idea was if you want to sample something special, you could move the bands around. Yeah, so that was a cool feature. But one thing, again, was that there was no tilting really for sun glint, and MERIS is a tricky. It's a very complicated. It's got a number of different focal planes, different cameras. So it can be tricky to characterize and characterize the sensor, because you've got basically I think it's millions of pixels, or millions of detectors across all these focal planes across like 5 or 6 cameras. So but they're smart people who do it. Okay, so anyhow, that's my little overview of sort of from there to now. We sort of went from the multispectral world where we were lucky to get an image of the entire planet in a whole 10 years worth of data to basically getting almost near daily global coverage maps of the Earth. And we've gone from just looking at things like chlorophyll right through to a number of these really interesting products. So moving into the PACE era, just sort of again comparing this graph here, this gives you an idea of comparing these multispectral missions to PACE. So multispectral channels are here, these little bars showing you where the channels were, and then PACE, we just put a color bar there because it's a contiguous hyperspectral. And I should say, some people define hyperspectral differently. So I guess hyperspectral, it's where we say hyperspectral PACE, we mean contiguous bands from 340 nanometers through to the near infrared, like about 900 at there's different, be about three, yeah, 2.5, 3 nanometer space, but each one of those has its own little bandwidth and whatnot. So, and PACE also has 7. This is a little bit old. We've got 7 SWIR channels actually, I think, on board in the end. Right. Sorry, I just get mesmerized by this. Trying to remember. So this is sort of more like the programmatic reason for PACE. PACE will, we're taking these legacy ocean color products that we've been looking at for the last 25 years and extending the climatology using a new and advanced sensor. So although we have VIIRS and ULTRI to do the job for us as well, PACE will do that, but in a new way with using new methodologies. As particularly the driver is to what we were talking about, phytoplankton community composition, is instead of just saying how much plankton's there, or someone likes to say how much carbon's being cooked, we're trying to ask who the chefs are. We're looking at we're trying to look at the community composition. And it is important to note, I know I mentioned before about these multi-mission sensor, but PACE is also, or multidiscipline center. PACE is also a multidiscipline sensor. PACE is also a multidiscipline sensor. There we go, I can't. But we obviously come from the ocean color background, but we also, the mission also carries 2 multi-angle polarimeters. So they're designed to work with the atmospheric scientists to derive atmospheric products. Okay. And we launched earlier this year. It was very good. It was a relief when the spacecraft went up aboard a Falcon 9 rocket from Cape Canaveral, and yeah, I've already described that bit there. You guys probably don't really need to know this, but you will be interacting with people on the project. So this is kind of the org chart. So actually, it's a little bit out of date. Paula has moved on, and that's Laura Lorenzoni as the program scientist. But essentially, we have people at headquarters. We have project science based at NASA Goddard, and there's these competed science and validation teams. And we also embedded within Goddard, we have what's called the science data segment. So that's the group that's responsible for bringing the data down, processing it, generating the products, serving them out. But most of the green boxes are within the NASA Ocean Ecology Lab. The yellow boxes are external, and the blue ones are down there at NASA headquarters, the programmatic sort of level. So there's a number of requirements for the mission when it was formulated. So the formulation of PACE sort of dates back to probably like the about 15 years ago. There was one of these decadal surveys that said, with the National Science Foundation, hey, we should have a hyperspectral sensor. Because we can advance the science and do new things. From there, NASA says, yes, okay, let's do that, but we have to prescribe the requirements for the mission, what it needs to do. So a lot of things are, NASA doesn't just build a satellite and go, yeah, let's just make an awesome satellite and get it to do everything. they have to formalize. This is what it's going to do. This is how it's going to work. This is the budget, etc. So essentially, we're looking at these are the required products, and they're not that much different from what we might be familiar with Modus or Veers. But where we're looking at advancing is going to this phytoplankton community composition. And I feel like maybe we've talked about this already, but have a look at these. So we talked about trichodesmium and diatoms yesterday. So I guess we can think, if we're thinking the functional level, like trichodesmium, let's think of in a trichodesmium can be thought of the phytoplankton that lives in tropical areas, and it's very important to the nitrogen budget, and also be a nuisance for it. Whereas let's say we've got some diatoms in an upwelling area, that might be a good thing because it becomes a very rich fishery. So let's just call it here fish food. So if we look at the, I should have covered this up. Oh no, sorry guys over there. If you can do it with you, cover up the hyperspectral graph and just look at this multispectral comparison of the absorption coefficient of those two phytoplankton. So again, imagining we created a PFT algorithm down the spectral route. Remember I was talking, there was two routes, the spectral route or the abundance route. Let's cover up this one here, pretend you can't see it. And for all intents and purposes, the multispectral absorption coefficients of these two very different phytoplankton look the same at 5 wavelengths. But then if we go to hyperspectral, you can see they're completely, they have different spectral signatures, which is great. And this is kind of the premise of doing this hyperspectral mission. There is signal in the hyperspectral measurements that will help us tease out these community groups. We've also, using the ultraviolet and our shortwave infrared channels, we can do better atmospheric correction, particularly in optically complex coastal waters where we know we have problems where. So I don't know if. So the premise of an atmospheric correction using the near infrared channels is what do we make? Let's imagine we're doing an atmospheric correction over the open ocean. We have these near infrared channels, and what is the assumption about the water leaving radiance in the near infrared for the open ocean? There's none, yeah. So there's none. So you assume that in the open ocean, near infrared, any contribution you're seeing from the satellite is from the atmosphere, and that sort of forms the basis of our atmospheric correction. But when you get into the optically complex waters, that's not true anymore. You get a non-zero near infrared signal. So you have to come up with other ways to do atmospheric correction. And one of them is to go even further out past the near infrared into the shortwave infrared. You can use those channels to, that's where it should be zero in the shortwave infrared. So then you can use that to extrapolate your assumptions about what the atmosphere should be doing. It can be, yeah. It depends what you're next to, and if there's an island in the middle of that pixel, maybe no. Good question. We also got these two new sensors, multi-angle polarimeters, and they're looking at atmospheric properties. And I'll talk about the data products in a second. But you know, the idea is that these three sensors can complement one another. Not here. Yes, and the idea is, yeah, polarimeters are going to help us. Typically in ocean color, we just say, the atmosphere. We think the atmosphere is this thick. You know, when we say aerosol optical thickness, you know, if you're looking between you and the sun, how thick is that atmosphere? What's the aerosol loading? If it's a small, it's a small number, it's very clear air. If it's a big number, it's very, you know, a lot of aerosol up there. With the polarimeters, you can go beyond that and sort of similar to what I'm talking about with plankton, that are saying just we can go beyond chlorophyll and go to phytoplankton groups. With the polarimeters, you can go beyond just saying this is how much aerosol there is. You can start saying this is the species of aerosol. So it might be soot or dust or smoke or volcanic ash. So there's not just science behind that. There's also end user application. You know, the aviation industry really would like to know if there's a volcanic ash plume and where it's going, for example, or human health. If there's a wildfire and there's smoke coming towards a populated area, it's useful to be able to monitor that. So Oh, anyway, most importantly, I think I've said it a number of times, the OCI, the Ocean Color Instrument, tilts, which means we can mitigate sun glint once again, as we did in the CWIFS era back in the 90s, and start getting back a larger number of valid pixels, particularly in like equatorial regions, where we've sort of been, I guess we've been undersampling a little bit because of the sun glint at a certain time of the year. Okay, so this was the path to launch. All I want to say is we've been up for 200, we haven't been even up for a year yet. When you build a spacecraft and a mission, there's a lot of like different steps. You have to design it. You have to do what's called trade studies. So you say, oh, we could build this type of sensor in this way. And then the engineers go and try and build it. And they say, oh, it's going to be very expensive. Do you think you could cut that little bit off? Or, you know, every moving part of a spacecraft, because you're in zero gravity, has to have a compensating momentum mechanism. So for example, PACE has a rotating telescope. And if it rotates this way, you've got to have another momentum wheel rotating the opposite direction so the spacecraft doesn't fly out of control. Same with when you're tilting the sensor fore and aft. As it's tilting, you have to have a mechanism that compensates for that tilt. So, and also it has to be very precise, because if you have any jitter as the spacecraft's maneuvering, you start to get blurred pixels, or you lose your geolocation goes off. So there's a lot of precision. Tilt was a lot of engineering. Kudos to the team that built it. It's a lot of thought and energy went into it. So anyway, we got to the point once it was designed, they said, yep, we're done. They started building it. Each little bit gets built separately. You have an optical team, you have a spacecraft team, a propulsion team, an electronics team, and then eventually it all comes together. And once everything starts being attached to the spacecraft, fun fact, it's no longer called spacecraft, it's called an observatory. And then they do all this spacecraft. Once it's up there, you can't fix it, right? So it's up there and something goes wrong. You can't just send someone out in a rocket to fix it. So prior to launch, you have to do a lot of what they call integration testing. So every component of the mission has to go into, essentially they call them like thermal testing, and so they will heat things up and cool them down to simulate the temperature fluctuations in space. They'll shake them, they'll put them in acoustic chambers and blast them with like big subwoofers, basically, boom, 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 to see if anything falls off, and hopefully it breaks in the testing. So then you can go, okay, let's fix that. Yes. No, that was Prism. Oh, sorry, that was half instrument. Yeah, the whole limit. So, but it was good though. Needed good for things to break on the ground, not so. Anyway, so integration and testing is fun, and then eventually every subcomponent gets put together, and they continue the testing, and then they put it in a big bus and big trailer, and they drove it down to Cape Canaveral, and they put it on the spacecraft, and up it went, and there it stays, hopefully healthy. And then we're here. We know that. Nice time lapse. So so with this Falcon 9 rocket, booster stage returns back down to Earth. So this is a time lapse of the rocket going up, and then the booster stage returning back down. So it's kind of fun to watch. Yeah. No, sorry. No. That's a very important question. Yeah, very important stuff. So no, so what we should say is there's these different phases of the mission. Phase F, that's the decommissioning phase, but that doesn't necessarily occur then. So what normally happens with these NASA missions is you get a 3-year prime mission. So we have 3 years to do our thing, show it works. And then typically what happens is you go for a senior review where they say, is everything working? And then the spacecraft actually has 10 years worth of propellant on board. So it can stay up for 10 years or slightly longer. MODIS is one of these sensors that just, is an example where it had a much shorter mission life, and they just kept extending it. So no, good question. We're not going to burn it up after 3 years. It's about 10 or so years, is maybe a bit longer. Like they're clever engineers who can squeeze Jeremy tells me that the bulk, you have it inside the box, I'll show you actually. Let's have a look at the spacecraft. You can skip past this stuff. So inside the spacecraft it's like a big box about the size of a Volkswagen Golf, and there's looks like a big silver keg of beer or something, but that's the hydrazine propellant. Jeremy tells me the bulk of that is to act for deorbiting. So you use some for rotating and moving the spacecraft in its plane. You usually use these momentum actuator wheels, and they spin and the spacecraft will roll. But if you have to lift the orbit or move it, if there's some debris or something, or every now and again, it's even though it's in 600 and something kilometers up, it's still the orbit starts to drift down, so you have to boost it back up every now and again. So, but yeah, so you got to make sure you got enough to get it back safely at the end, so it doesn't become a piece of space junk. No, apparently Meris is like a chaotic school bus that's just MVSat is just flying around somewhere in outer space because it just. So you want to try these days. We try and make sure our spacecraft, when they're finished, they come back safely. So, okay. Anyway, that's what the OCI looks like. It's quite large. The OCI, it's quite a large instrument. This is where the light comes into the sensor. Your rotating telescope. This on the side is a big radiator because you want to. What do you reckon you need a radiator on a spacecraft? And it faces always faces away from the sun, always out to dark space. You want to keep your detectors cold, especially SWIR detectors. They need to be kept really cold. So like if people are doing astronomy in the old days, they still do. I think in astronomy, they often will have their detectors cooled with liquid nitrogen inside the these big telescopes in their domes. So yeah, it looks like it's wearing a big hat or something like that. So we sort of know what it is, a hyperspectral sensor. 1 to 2 day global coverage. We can tilt. We do these lunar calibrations, and we have an onboard solar calibrator. And importantly, I'll show you the signal to noises in a minute. They're optimized for the ocean and trying to make sure the sensor doesn't saturate if you go over a cloud. Because cloud, you're looking at a dark ocean, then all of a sudden you look at a bright cloud. You don't want things to saturate. Wayne showed this the other day, so I won't really go into it too much, but essentially you have this is what the optics look like at the back. You have a mirror, a rotating telescope at the front, which then sends a signal down to a half angle mirror, which then reflects it into the rear optics. It hits it's called a dichroic mirror. So all the blue light, goes from about 340 to 500 something nanometers, goes down into this focal plane, then the rest from the red end goes down into the red channel, and then the shortwave infrared goes to a completely separate subassembly of detectors. And I guess I put this in because it's sort of a lot of people you're not aware a rotating telescope is a very signal. They call it signal poor system or photon. It's not photon rich, it's photon starved is what they say. So often people say, well, how do you boost this? How do you get good enough signal to noise if there's not enough light coming into the system? And the way they do this is with an approach called time delay integration. So the detector actually sees 16 sites. So your 1 kilometer pixels actually split up into 16 little pieces, or the detector has 16 bits as it scans across, and as the rotating telescope goes across, I'll show you the animation instead of trying to explain it. So, how does a rotating telescope work? You're looking through your viewport down at the ocean. This is remember I said the shiny washing machine. It looks like a brown tub, and as it spins round, you see the ocean scene is reflected off the inside of this mirror down onto a mirror that rotates at about half the angular velocity, half the angular speed as the rotating telescope, and then it's reflected through the slit and into those optics at the back, like I showed. So as you kind of animate it, that's what it looks like. You can see that half angle mirror is spinning half the rate. And once you for each of those, we talked about the grating. You kind of signals split up into these spectral channels after it goes through the grating, and there's this little slit that is imaged as it goes across. So yeah, this is the bit that is really interesting. It's called the time delay integration. So you have 16 detectors across the field of view, and what happens is as the image is sort of scanned, you for example, as you're scanning through, you see the same pixel, same viewpoint on Earth 16 times, and then it's read off 16 different times and aggregated up to boost the signal to noise. And I'll try and show this cartoon to see how it works. So let's imagine we're viewing the same point. The little grey dot there is the same point on the Earth, and as we're moving across the scene, we're measuring it 16 times, and then that's read off the detectors and aggregated up to boost the signal to noise. I'm not very good at explaining it. So, yes. Yeah. It's like probably nanoseconds or milliseconds. It's very fast. So, yeah, I mean, I think someone said that conceptually you could, instead of aggregating those, you could treat each one of those as an independent pixel. So you could end up with 1 kilometer wide pixels, but they have 16 little sliced up at lower signal time. Yeah, but it's very fast. But it has to be timed perfectly. So there's a lot of work went in the background. Anyway, so the result is that PACE has got excellent signal to noise. The signal to noise we're aiming for the ocean for this mission, roughly about 1,000, what we're looking for, and making sure that it doesn't saturate when we hit a bright target. So up here on the top panel, you see this is the signal to noise in the blue channels, and we're sort of well above the 1,000, 1,000, and in the red, we was a bit relaxed. We knew that the ocean is a bit darker in the red, so the signal to noise would be a bit lower and just spectral limitations. But the important thing to look at was this one down the bottom, where we're looking at making sure we weren't saturating the sensor, which we don't. Thankfully, there's only a few places where we would saturate under very, very extreme conditions, which is quite incredible. So just basically summing up, saying we have a very sensitive hyperspectral scanner that is robust to a huge dynamic range, which is, it's a bit like if you get up in the middle of the night and turn the light on and it takes you a while for your eyes to adjust. You don't want your sensor to do that if it sees a bright cloud. You don't want to go from looking at a very dark ocean to looking at a bright cloud, and all of a sudden it takes time for it to bounce back. So, okay, I'm going to go through these ones quickly. But so the specs one is it is a contributed polar emitter from Esron Airbus, the Netherlands. Now it's a CubeSat size, so it's probably not much bigger than, size-wise, not much bigger than this, and it just sort of sits on the side of the spacecraft. And it's a nice complement for PACE because it's hyperspectral, and it looks out at multiple different angles. Sorry, this one's this one is multi-angle. So essentially, what the idea of the multi-angle polar emitters is, you want to view the same pixel, but as the spacecraft flies over, you're looking at it through different directions through the atmosphere. So it's a bit like, so you're looking at multiple angles. First off, if you've got 5 angles and you have multi-angle polar emitter, that one's looking at it, and as you fly over, this one looks at the same pixel. And obviously, there's a lot of thought has to go into co-registering which pixel you're looking at, and essentially we have to come up with a new gridding technique called that's a level 1C grid. So level 1C grid is sort of a spatially consistent, making sure that all your view angles, you have multiple views of the same pixel, but you've got to make sure they're all within the same bin. So you do a little bit of spatial magic. The ground pixel size on there's a lot of data comes down from SPEX1 because it's hyperspectral. So, and you're looking from different angles. So the trade-off is it's quite a narrow swath width, about 100 kilometers wide, whereas if you're thinking about OCI, it's thousands of kilometers, like 2,500 kilometers wide. So anyhow, this is a really cool instrument. The objective there is to look at aerosol properties beyond what we can see with OCI. Like I said, starting to get to the aerosol species. The HARP2 is the second contributed polarimeter. This is from the University of Baltimore County. This is the one you mentioned that there was a part of this got well, not damaged, but it broke. It was fixed before it went up, so that was good. And this one it's kind of a cool sensor. It's a bit like a fisheye lens with like these stacked filters, or with these little filters inside. There's no moving parts. Same with SPEX1, there's no moving parts. It's very, very sort of robust little sensor. But unlike SPEX1, it's multi-spectral, and the trade-off is it's multi-spectral because it looks at a lot of different angles, and it has very good polarimetric accuracy. But the objective for this one is it'll be focused a lot on cloud properties, looking at and ice particle shape. So you've got one that's looking at aerosols, one that's looking at clouds, plus complemented with PACE. It's a good package. Okay, so this is what PACE looked like before it went up. Like I mentioned, this is about the height is about the size of a Volkswagen or a compact car, and you've got as you're looking at it right now, direction of flight is into the ground. The Earth is that way behind you. The sun is out that way because the solar panels are tucked away, and the darkness of space is on the right-hand side. That's where your radiator is. PACE is up on the top here beside the radiator. That is SPEX1 is the little red box, and HARP2 is sitting there just above SPEX1. So it's a pretty compact spacecraft. On the big white sort of looks like a dinner plate on the side. That's the antenna. That's the Ka band antenna. So we need a Ka bands. John's going to ask me what frequency it is, and I can't remember. John, what frequency is Ka? The Ka band's a very fast sensor, so we need fast downlink, and so PACE will downlinks. Spanish, I'll get it correct. Punta Arenas in South America, right down the bottom, and also in Alaska. So you get two downlink opportunities because obviously we're collecting so much data. We've got to get it down, and it's sort of there's a very quick latency between getting it down. It goes to Goddard, gets processed really quickly, but it's got enough onboard storage if you miss a downlink. Oh, and there's Jeremy. Jeremy's project scientist. I don't know if anyone's met Jeremy before. And don't worry, he's not touching the actual spacecraft. This is what they call a mass model, where you make the testing. You have to make a spacecraft that has the exact same dimensions and the exact same mass. So you can it's called a mass model. So we were allowed to touch. Not allowed to touch the other one without wearing a bunny rabbit suit. Okay, I'm going to send a little animation on here because I need to have a drink of water. And this is just an animation of a day in the life of PACE. Like it's an ascending orbit. It's inclined slightly, 98 degrees inclination, and we're up at 676.5 kilometers. This gives you an idea of what the swath width is like on PACE, and shows as we're about to go up over the equator, we tilt the spacecraft to avoid sun glint. And they stagger where they do that day to day, so you don't always end up with a strip of missing data around the equator. Then we have HARP2. That's that the hyperspectral angle polarimeter, and you can see that gives you an idea of the view angles, and the swap width. It matches very closely to pace, but the pixel size is a bit coarser. Space there, and then specs one, you can see it's a very, very narrow swath width, but it's hyperspectral, and there's a lot of data coming down with 5 view angles, and its pixel size is closer to pace at 2.5 sort of kilometers. So specs one, actually, I think it's closer to like the order of a month, whereas the others it's within 2 days. Yeah, it's quite 30 days. Probably because the first time I played this, a little bit slow. So this sort of gives you an idea of, as well, when we're looking at some satellite data this afternoon, this kind of gives you an idea of what we call swath resolution data. So we take these big beach, like I like to call it a beach. It looks like a beach ball. You take these strips of data that are imaged of a sphere, but as we get them back, they're obviously not curved. You can't curve a 2-dimensional image. You get this swath resolution image that's broken up into bits, and then we have to remap it and bin it, and so we can make these kind of really cool animations. Let's move on. So I just wanted to put a note in on calibration. So as with who uses, remind me, the field scientists here are using instrumentation in the field. Right, so how often do you have to calibrate your instruments? A lot. And how do you do it? Send to the manufacturer, or you put some sort of reference material? That is doable. We can't, but once pace is on orbit, we calibrate it before it goes up. But once it's up, we can't send it back to the manufacturer for calibration. So we have to come up with a few tricks and how to calibrate. So we look at standards like, in this case, we have solar calibration. So we don't fry the sensor. There's a diffuser where the light comes in, and we measure that. And you can treat it as sort of a quasi-stable, but sort of quasi-stable source lamp, if you will. And then the other thing we do is we look at the moon, because the moon is pretty uniform when it's full. We only get a look at the moon every month. And what happens is the spacecraft actually does a maneuver where it flips on its back. It looks at the moon, and then we use a computer model of what we think the lunar radiance should be, essentially compare the two and work out, compared to the starting point of the mission, the degradation of the sensors. And you get these kind of, downward, because once things go in space is a harsh environment, things start to degrade, and it's just the name of the game. You just have to track that degradation really well. The other thing we have to do is what's called system vicarious calibration. And what that is, essentially, you take a very, very good measurement of water leaving radiances in the ocean. PACE has 2 different ways to do this. We have what's called the hypernav, which are I like to call them the copepod, because they look like a little zooplankton with antennas, but those are upwelling radiance sensors, and it sort of goes up and down in the water column, measuring the upward radiance distribution, and then you can extrapolate that out through the water column and compare that to the satellite. We also have another sensor called MOBI, the Marine Optical Buoy System, which has been around for a while now, based off Hawaii. You guys go out and sample? Yeah, MOBI. I know that sometimes people tie their boats up to it, and then it gets drifted away, and they have to go and bring it back to the mooring because the line gets cut or something. It's a good fishing spot too, apparently. Yeah. I'm not condoning people go fishing there. So again, it's a similar principle. You've got these radiometers measuring the upward light distribution. The trick is with something like, well, I guess the trick is with MOBI, it's hard to measure the upward radiance distribution, or you're measuring, essentially what you do is you measure the upward diffuse attenuation coefficient, and then you try and extrapolate out through the water column. But at the red end, that becomes tricky, because there's a big difference between what's happening with red light down here and up there. But that's a whole discipline in itself, and the hypernav kind of addresses some of those challenges. And then you end up putting your data into this vicarious calibration system, where you're comparing the field measurements with the satellite measurements, and then you essentially come up with a series of coefficients to correct your satellite radiometry so that your reflectances from the satellite are matching the field measurements very, very well. That's just an example of a flow chart they use for the SGLI sensor. Don't pay attention, you'll fall asleep. No, that's not saying anything bad against Jackson, just saying I think most people have had enough equations today. Okay, so getting into sort of the tail end now, data products and distribution. That might be what you guys are more interested in. What are we doing with PACE? As I mentioned, it's a multidiscipline mission. So we've got atmospheric and oceanic products. It's because when we're at the top of atmosphere over the ocean, we're seeing not just the ocean signal, we're seeing that aerosol signal as well. We're looking at obviously the legacy aerosol products you might be familiar with, like aerosol optical depth, aerosol optical thickness, but then going into the speciation of the brown and black carbon. So me being, there's obviously application for this, and scientists, we want to know about the aerosol types. For me, I see this as an opportunity to improve our atmospheric correction. As I mentioned, a lot of our atmospheric corrections don't always take into account absorbing aerosols really well, and that's these sort of brown and black carbon. In coastal areas, that becomes a challenge. We're looking at a number of cloud properties and things like BRDF and angular distribution of light from the surface. This is something that you can start to, if there's a change in the BRDF, it might indicate something like an oil slick present. So getting down into the water column, the usual suspects like light availability at depth is a big thing. So PAR at depth, the angular distribution of those light indices, and pulling all this information together to try and get phytoplankton pigments or primary productivity, and carbon, what's happening there. And someone like John, I put that one on bathymetry because although it's very coarse pixel size, it's still something that people over the macro scale, sort of large areas, are interested in doing. For me, I want the IOPs above stand. I don't really care about the stand. And we're also doing a limited number of LAMP products, even though they're not required, but doing some pretty cool stuff actually with that. Okay, if you go to the website, there's these very extensive tables that tell you what data products we're distributing, and also the ones that are in development. So we have a science team who is actively developing new approaches and new products. So many of the ones we had at launch are what we call legacy algorithms. We've been doing the same thing for a long time. We're now stepping it up to innovate with these new data products. So that's where you can learn about these things. We have a formalized process of implementing our algorithms now. It's called the data product selection plan. So in the past, in the CWIS days, it was just sort of people working together, come out with new ideas. But I think there's a lot of algorithms out there now, so we kind of have to vet them. So we have more of a formal process to go. We get an algorithm might come in from, say, our science team. We test it, evaluate it, see if it's working. Sometimes an algorithm is not computationally efficient, for example, or the way we're implemented it is not working in the correct way. So we have a bit of to and fro with the algorithm developer. And if everything works well and it meets the expectations, it becomes what we call a provisional product. And then eventually, if it supersedes, it reaches the point where it supersedes our old data product and it's working really well, then it becomes like our standard product that we would distribute. Now we're now putting all of our algorithm theoretical basis documents. That's where you come up with anyone rather than me explain. Who's heard of an ATBD before? So, John, what's an ATBD? I need to have a drink of water. Yep. How'd you know? Thank you, Annie. Yeah, so the idea with the ATBDs is that if you're an end user, and you use these data products, but it needs to be transparent. How do we make them? How were they validated? What's the science behind them? So we've got this new system for publishing our algorithm theoretical basis documents, which is called Earth Data APT, algorithm publication tool. So that's where some people when the mission launched are like, where did the diffuse attenuation coefficient ATBD go? It's gone. Well, no, it lives here now. Same with all our IOPs and biogeochemistry, and we're migrating all of our ATBDs into there now, and they'll be easier to maintain them, keep them more of a living document as incremental changes happen. Whereas in the past, they were written as a PDF and put into a NASA tech memo, which you have to revise it. It's a long process. So, okay, the PACE data is available now. I'm not going to even bother with the slide because I'm going to show you where to get it from later this afternoon. Again, that one, CDAS, I'm going to talk to you about that this afternoon. But I did want to mention how we're validating products. It's very formalized. There's this document called PACE validation plan. So it describes, after we've launched, how we're going to collect the data, what data we need, and how we're going to compare the field measurements with the satellite measurements and then report it back to you. So it's been formalized, but we're well underway here. We have a PACE validation science team which has been selected. A lot of them are currently out in the field. Now we've got someone who's part of it. Can we say you're part of the PVST, right? Yeah, someone who's part of the PVST in the room. And you're part of the PVST. Well, okay, awesome. So we've got people out actively collecting data, and it's a global data set too. So we've got from Hawaii to the Great Lakes, and I think they did a cruise off the coast of India earlier in the year as well. So that's fantastic. The other thing that's just happened is the PACE airborne experiment, which was off the coast of California. So as I mentioned, it's a multidiscipline mission. We at the oceanography side of things, I get an idea of how we have to validate our ocean data products, but the atmospheric products tend to be they're a bit tricky. So some of them you need to have an aircraft flying with a bunch of sensors underneath where the satellite's passing. So we have and at different altitudes. So they had like a Twin Otter, a tiny sort of low altitude plane, and then they had an ER2, which is a high altitude plane. Have you ever, the old spy planes the US used to have that fly very, very, like almost above the atmosphere, almost like on the edge of space? Well, that's basically what an ER2 is, but it's a science one. So the pilot has to put on a suit and everything to fly. Pretty cool. And then you put all your instruments in the wing pods. So it's a good analog for a satellite. So that's already been out, and there's a bunch of data that's just coming through now, and everyone's going excited, but wow, we've got a lot. Just to give that's just an idea of where we're going globally with our PVST data sets. Someone's on the way down to where are they off to? In the South Pacific somewhere. Tahiti, yeah. So right now there's a group going down to Tahiti from Hawaii. We've got AMT data sets will be coming in, and then data sets from all around the United States as well. So it's it's exciting times. And there's that picture of that. There's a picture of those planes, the ER2 white one. Okay, so I mentioned system vicarious calibration. We've got those two sensors, which I showed you earlier. And David Antoine has just left, is in charge of this Marinet. There's one of those optical buoys that's permanently off Hawaii, and there's another one that is being deployed off the coast of Western Australia. So, got questions about that? Ask David. Okay, we have a applications office. So if you're more in the applied science side, you want to take in the data sets to be used in whatever problem you're asking or whatever problem you have, you can sort of use the applications office as a little bit of a mediation between the scientists and you on the outside. And Morgan McKinna is in charge of that at NASA Goddard. And just to give you a look at some sample data products. So this was a true, remember this, just want to say, caveat here, PACE. So we haven't done any the data sets I'm going to show you are were before we did any vicarious calibration. So our reflectances are still not perfect. There's currently a new reprocessing of version 3 reprocessing of paste data coming along soon. So just take it with a, we're pretty happy with it. This was pretty much straight after launch. But yeah, so this is an example. This is the Patagonian shelf of South America, and this is a true color image from paste. So yeah, remarkably beautiful features. It's resolving different phytoplankton intensities, the oceanographic sort of filaments and circulations that it's resolving is fantastic. And then if we look at this is one of the first chlorophyll ocean color images we looked at, which was pretty remarkable as well. Some of the things that I would point out here that is important you might not think about when I'm showing you this, is that there's no striping artifacts in the image. There's no speckling. And sometimes what happens is someone spoke about adjacency effects recently. So adjacency is where you might see a bright cloud and all of a sudden the sense it's like, like yesterday when I was getting some photographs taken of me and I was getting blinded by the flash, and it takes your eyes a while to adjust. That happens with the satellites too. So sometimes you get areas around the edges of the clouds that look a bit weird. They might have bright, like a halo effect. And we've seen with paste, we're not really getting that, which is great because it means it's doing its job. You're getting a very sharp line around those clouds and then straight back to seeing the ocean. And it should be scanning, I think, scanning this direction. Here's an example of just a composite of this is the Benguela upwelling in South Africa, and just sort of splitting the image up into taking a paste image, making the true color, and then we've got an algorithm, a PFT algorithm. I think this is the Milana algorithm, where you're splitting between two types of plankton, and then we just sliced in the chlorophyll on the other side, just to say we're going from we're producing the legacy products, but we're moving towards these new advanced products, which is pretty cool. Give you an idea, this is I think this is a day's worth of OCI data and VIIRS data globally. You can see that they agree really well, which is great. And this was one of the first. I know in science we call it cherry picking when we pick one thing that looks really good and put it in a presentation. But there was more data that we sort of extracted. But this was a reflectance spectral we took not long after launch. So we hadn't done vicarious calibration. We were still figuring it all out. And so Amir Ibrahim, who's in charge of the reflectance products and the atmospheric correction, put this together. So that's a comparison of PACE and VIIRS just for one science pixel in amongst all that. But it was just, the agreement was really remarkable. Like sometimes behind the scene, I guess what I've been trying to say today, and if you walk out of this room, one thing, please appreciate how much work goes into making these data products behind the scenes at NASA Goddard and at EU METSAT or JAXA, wherever you're getting your data from. There's a lot of corrections, calibrations. When something goes wrong, you've got to fix it. Thinking about how the algorithms are implemented, how we're processing. So anyway, there's a lot goes into making this. So seeing these results early on was really, really exciting. And here's another example of looking at a eutrophic lake. So the freshwater people here might get excited about this. This was paste reflectance spectra compared again to VIIRS, just sort of showing was very good agreement. And this is basically off the shelf without doing too much to it. So very, very pleased we were, and it's just going to keep getting better. Oh, I think it moves. Sorry, I think that was sorry, that's a GIF. A GIF, how do you say it? Yeah. Moves. This is CDAS. We'll be using CDAS later on. So just showing that there's pretty good agreement across. That's not just one, not cherry picking one. So in this scenario here, this was a very yeah, like hypertrophic sort of condition. I think it was really green. So, but I can't remember where that lake is. I did look it up. Maybe it's in the notes of the presentation. Yeah, it was got a lovely fluorescent red edge there. Yeah, the chlorophyll retrievals and OCI data agree really well on global scales. But one thing that pops out here is, remember I said VIIRS doesn't tilt to avoid sun glint, whereas OCI does. So OCI pace is on the right-hand side, VIIRS is on the left. Can you see all these like elongated strips where there's data missing? I mean, that look oval in shape. That's your sun glint. Whereas with the pace, you've got the tilt. So you're again, this is just one day, so you've got a bit of a strip of missing data around the equator from where the tilt is not collecting data. But we managed to recuperate a lot of, I think it's millions of pixels each day. So yeah, on average, we get 31% more pixels than VIIRS because we tilt and we're avoiding sun glint, and 60% more than motorcycle. So that's a huge amount. Even just if you, I'm a big proponent of tilt. I've said tilt a lot in this presentation, but I feel like it's a fantastic thing. So we've got some aerosol data products there. So we've got a dust plume. This is from the I think this is OCI products as well, and this is looking at some HARP polarimetry microphysical properties. We're looking at fine mode fraction of aerosol optical depth here. So where it's red, there's a very high aerosol loading, and you're seeing the fine mode fraction of the aerosol. So again, it's a bit like size distribution. It can tell you a little bit about what aerosols are present. This is a SPEX1 image, just sort of showing you these various aerosol retrievals over Japan and Ethiopia. You're looking at coastal waters over here in Japan, so we're getting around Tokyo. You can see there's a fine mode aerosol lighting up here, but not as much absorption. Absorption tends to indicate that you've got some sort of brown carbon or like smoke or soot in the air, whereas when we're over Ethiopia, over the land, you're seeing a lot more absorption there. So just showing you that we're starting to be able to use in the preliminary stages, these aerosol products as well are telling us stuff. So, okay, I am done.